Welcome to today's discussion of the normal approximation for probability histograms. This sounds like a mouthful, but as you see, we've got just a couple of essential concepts underpinning today's topic. We're going to unpack probability calculations in terms of sums, the primary statistic we've been discussing, and apply that to thinking about the histograms and normal curve for these sums across multiple trials. So our key idea here is going to be the probability histogram. And so get ready to look at a lot of probability histograms today. We've got a lot of visuals in today's lecture. So put your thinking glasses on and get ready. But first, let's think about a little problem. We have 5 tosses of a coin. And the idea here, just to help us get ready to conceptualize this whole topic, is to think about how when you toss a coin, let's say 5 times, but really any number of times, when you toss a coin 5 times, you can get a number of patterns that correspond to any given number of heads. So let's say, as we do here, that our given number of heads is 0. Then there's one way to get 0 heads. There's just the one pattern. And we can see there's various patterns, but let's really unpack this by looking at the scenario where we have 4 heads. And when we toss the coin 5 times, there are 5 different patterns that can lead to an observation, an observed value of 4 heads. So table 1 here shows how many patterns there are for any given number of heads. And there are, with 5 tosses, a total of 2 to the 5th, which is 32 possible combinations. Why 235? Well, there's 2 outcomes when you toss a coin, heads or tails. There's 5 coins. So this is where this number comes from. And we're just going to get a general overview here. I mean, really the take-home message from all of the things we're going to talk about in this chapter is most important to take home the ideas about applying the probability histogram to the normal curve. So this is just getting us started. You can see that when we have 4 heads, there's 5 different ways. We could have a tail first, a tail second, a tail third, fourth, or fifth. And any of these ways, any of these possible patterns will give us 4 heads. There's 5 patterns, okay? Now, if we look at the chance of 50 heads in 100 tosses of a coin, you can see there's the same mathematical pattern. The number of patterns has a given number of heads for any number of tosses. So when we have 100 tosses, the number of patterns is now 2 to 100, the 100th power. So that is a huge number to calculate, though, and don't worry, you won't need to calculate all of that. But if we go through and just think through the mathematics here, we can say mathematicians, of course, have worked this out. And when you do it mathematically, looks like this. You don't really need to worry about the math here. I'm just showing it to give you the whole deduction. So this gives us a the number of patterns with exactly 50 heads. That's what this number is. Now, our next quantity here is the total number of patterns, 2 to 100. Okay, this is our total number of patterns. So if we want to get to the number of patterns with 50 heads, we need to, if we want to get to the percentage of our patterns with 50 heads, then we need to use a ratio of the number of patterns with 50 heads to the total number of patterns. And you see that's how they end up with 8% chance of getting 50 heads in 100 tosses of a coin. One final point here is that the procedures that led to deriving this de Moivre had led this researcher to the normal curve. And actually, this isn't theorist, but for he found that the chance of getting exactly 50 heads was about equal to an area under the curve between negative 0.1 and positive 0.1. And he's able to prove that by looking at the whole probability histogram for the number of heads. And he determined that it's close to the normal curve when, and this is crucial, when the number of tosses is large. And so we've extended this idea to the sum of draws made at random from any box of tickets. And as you'll see, we've extended this idea even further to random sampling techniques. Chance process underlies coin flipping or dice tossing, and that's why we are using these simple models of tossing a coin or a die or pulling tickets from a box. They all represent a chance process, a random process. And when a chance process generates a number, the expected value and the standard error are a guide to where that number will be. It's not enough to say, when you're dealing with a chance process, that you found the expected value. It's really essential to know the standard error, which helps to give you a rubric, a guideline for estimating what interval your sample observed value will likely be in. And we'll get into this idea of confidence intervals later in this unit, but they are, and it's an important idea because an observed value, an expected value, or a value is not just freestanding. The expected value needs the standard error to be meaningful. The standard error gives you a better idea of how the expected value is going to operate in the random process of sampling. To really complete the picture, though, the probability histogram is another essential piece. And as we know, the probability histogram and the shape of the normal distribution is intricately or inextricably linked with the standard error. The important idea here to remember is that we're not just talking about any histogram. A probability histogram represents chance, not actual data. So back in the beginning of the course, we made a lot of histograms. They represented actual data, not just probabilities expected. And this is a really crucial piece that we're going to carry through this section, this unit, and our next unit, this idea of chance under the curve. The chance is represented by area under the curve. So let's look at a distribution of spots. Let's see this in action. Why does it matter when our chance process gets more repetitions? It's random. So remember that when we have a smaller number of trials in a random process, we're more likely to see variable scores. We need to increase the number of repetitions to get a good representative distribution of our expected probabilities. But what we're looking at right now are our actual observed probabilities. So you can see this is an empirical histogram. And this empirical histogram is distinct from a probability histogram. We'll get to a probability histogram though. When we look at this empirical histogram, we've got the total number of spots on 2 dice. So somebody or a computer rolled a dice twice, 2 dice, 100 times. You roll the dice once, add up the spots. Roll it again, add up the spots. Okay, we do it 100 times. And as you can see, it doesn't quite look like a normal distribution yet. What if we increase the number of times we roll our dice, our number of observations, to 1,000? When we get to 1,000 observations, you can see that this much more closely resembles a normal distribution. This is still, of course, an empirical histogram. And if we go even further and toss the dice 10,000 times, so we have 10,000 repetitions now, we have an empirical histogram that very closely resembles our probability histogram, as you can see. The probability histogram is the ideal for the total number of spots when a pair of dice are rolled. But as we know, things do not always go in an ideal way or as planned. So we can use a probability histogram to predict the chance of certain scores or certain ranges of scores, but that doesn't guarantee we're going to see those scores. What we're getting is a prediction or a probability of based on the normal distribution. For example, if we rolled the dice many times, as you could see, but for each roll of the dice, let's say that like this, for each roll of the dice, there's several different ways to get 7. As you can see, 7 is your most likely sum, probably why it's one of the target numbers when you play craps. And however, it's not necessary to get to 7 through a specific path. We could get to 7 by 6 plus 1. We could get to 7 through rolling a 2 and a 5, a 3 and a 4. You can see there's multiple ways to get to 7, and we don't know when we say predict, if we said, what's the chance of getting a score of 7? We don't know the process that it got to a score of 7. It's a random process. So we may not know if this individual 7s represent 5 plus 2 or 3 plus 4. We can only observe that they summed to 7, and our random process assures us that if we tossed dice thousands of times, the number of spots summed would represent a probability histogram like this. Let's look at an example of a probability histogram for the sum of 25 draws from the box 1, 2, 3, 4, 5. The shaded area represents the chance that the sum will be between, and this is helping us think through using our probability histogram functionally. So now we're being asked for the chance that the sum will be between in this shaded area inclusive. Inclusive means you're including the scores that are at the edge. So we can see that this shaded area goes from 70 to 80. This is distinct from when we have exclusive ways of breaking down histograms. So let's just look quickly through these examples. You can see in the bottom corner here, this is, oops. Oh shoot, sorry about that. This is figure 1. We were just looking at it in smaller pieces. So the chance that the total number of spots will be between 7 and 10 equals the area under the histogram between. So we're looking at the bottom figure here, between 7 and 10. So from 7 to 10. The area representing the chance for these scores, if we want to be inclusive, is going to go from 6.5, because we need to take the midpoint of a score that's not part of or not available in the sample, through 10.5. And this is the interval, oops, shoot. This is the interval that we're looking for. And remember, the question is just asking not for the exact probability of the interval, but just the area under the histogram between these points. So between 6.5 and 10.5, because it's inclusive. We need to include 7 and 10 in our measurement. The chance that the total number of spots will be 7 equals the area under the histogram, again, between 6.5 and now 7.5, which would be about here. Here's 6.5. Sorry, my marks were a little off on that. The bottom part of my screen is quite difficult to see, as you know. So just a couple more exercises to help us think through this. We have a pair of dice that are rolled. A total number of spots is most likely to be, of course, it's 7. We already have seen that. There we go. Yeah, thanks. So let's look at B. In 1,000 rolls of the pair of dice, which total is going to be most common or come up most often? Now, we've got 7 again. 7 came up most often, and this is no surprise. In the top panel, the rectangle over 4 is bigger than the rectangle over 5. Do you think that's because 4 is more likely than 5? Should we now start betting on 4? No, 4 is not any more likely than 5. It's this is just chance error, and that's why we have to account for many repetitions. See, many repetitions before we get to a probability histogram that actually represents the ideal probabilities observed, or expected, rather. So if we look at, again, finally, the top panel, we can see the area over 8 represents one of these, the chance of getting a total of 8 spots when a pair of dice are rolled, the chance of getting 8 spots when 100 dice are rolled, or the percentage of times the total of 8 comes up. Sure, we'll say it's water. I'm just kidding. It is, except for when it's tea. So we have 8 spots. What does this represent? It can't be the chance of getting a total of 8 spots when a pair of dice are rolled, because this is for 100 repetitions. Is it the chance of getting a total of 8 spots when 100 dice are rolled? Not exactly, because this is an empirical histogram. This represents actual data. It does not represent probabilities. Only the probability histogram represents probability. This empirical histogram just tells us the percentage of times a total of 8 comes up in table 2. That's it. This is based on the actual data and not percentages, or not, excuse me, probability. It just helps us in determining the probabilities. So as you can see, there's some interesting applications of the probability histograms in the normal curve. The probability histogram for the number of heads gets close to the normal curve when the number of tosses becomes large enough. Remember, when the coin is tossed 100 times, the histogram for the number of heads is a bit jagged, but it follows the normal curve still pretty well. Oh, I have it here, as we'll see in a moment. So as you can see, we've got 100 tosses, and the probability histogram is kind of jagged, but you can see that it still is distributed as a normal curve. Now we can see, comparing the number of tosses for 100, 400, and 900, the histograms for various numbers of tosses. And as you can see, the more tosses we have, the more samples, trials in our sample here, we have a better and better normal approximation in the histogram. So let's think about the normal approximation a little bit, because using the normal approximation is so important throughout this course. As I'm sure you can already tell, we've used the normal approximation in chapter 5 to help us get probabilities under the curve, just at a basic level. Then we used it again in chapter 17 to figure probabilities across trials. Now we're looking at the logic behind those uses. When thinking through the logic of these uses, it's important to remember that the endpoints can be a little bit tricky. So we have a technique for taking care of the endpoints, which you can use when there's a small number of tosses or extra accuracy is needed. As you know, sometimes it's important to have very accurate data, especially those of you who are in the health, nursing, or health science. Oftentimes, it's important to be very accurate. You know, slight difference can be crucial. So when we have still looking at our coin tossed 100 times, we can think through first the chance of getting exactly 50 heads. And you can see this worked out here. The expected number of heads when you toss the coin 100 times is 50, and the standard error is 5, as you can see down here. Oops, these are our standard units. You can see it on page 301. We've figured these out extensively in our last lecture. But now we're looking at our histogram. And so if we want to use our histogram to find the chance of getting exactly 50 heads, remember that's different than just getting our expected number and the standard error. We want to get a chance, a probability, and that can be a very powerful thing. And that equals the area of the rectangle over 50. As you can see, the base of the rectangle goes from 49.5 to 50.5 because we want this whole area, that we want the complete area that encompasses 50. We can convert these boundaries to standard units, as you see, and the standard units become negative 0.1 and a positive 0.1. When we go and look up this area, when we go and look up this area on our Z table, we can see that it's going to be equal to 7.97%. So there's a 7.9% chance of getting exactly 50 heads. And when we think about endpoints some more, you can see another example here where we're looking for the chance of getting between 45 and 55 inclusive. And again, we've expanded our boundaries down to 44.5 and up to 55.5. So we include the scores that the whole area of interest, convert to z-scores, and get the area between those z-scores. However, oftentimes it's not specified whether the endpoints are included or not. The problem might only ask for the chance that the number of heads is between 45 and 55 without specifying about the endpoints. In that case, you can use the compromise procedure, and most of the or many of the questions in this class will use the compromise procedure. This is pretty common, and this amounts to replacing the area under the histogram between 45 and 55 by the area under the normal curve, corresponding between the corresponding values. Thus, we end up splitting the two end rectangles in half, and it doesn't give quite as much precision, but it's still very effective. And usually the exercises can be worked using the compromise procedure. Like I said, keeping track of the endpoints, as we did previously, does have an official name. It's called the continuity correction. It's worthwhile if the rectangles are very big or if a lot of precision is needed, but we won't spend much time on the continuity correction, and it's important to be aware of, but I wouldn't worry about it too much in terms of exam topics, for example. So let's just make sure we fully understand what we're doing in our compromise procedure here. When we use this compromise, the normal approximation allows us consists of replacing the actual probability histogram by our normal curve before computing the areas, but this is only legitimate when the probability histogram follows the normal curve. Probability histograms can be hard to work out, but areas under the normal curve can be quite easy to look up in a table. So it's important before you jump into using a compromise procedure to assess whether the normal approximation is appropriate. So and let's just get a little practice here with our thinking through just identifying this inclusive exclusive. We have 3 shaded areas. 1 is the chance of getting 3 to 7 heads inclusive, 3 to 7 heads exclusive, and getting exactly 6 heads. Well, this third one is quite easy to see. Exactly 6 heads is clearly got to be 1. When we look at histogram 2 here, we can see that 3 and 7 are not shaded, so this must be 3 to 7 heads exclusive, excluding 3 and 7. And finally, we can see that this one is clearly inclusive because it does include 3 and 7. In the preceding section, the discussion was about a coin, which lands head or tails with a chance of about 50%. What if we were drawing from a box? Again, the normal approximation works pretty well as long as you remember that the more the histogram of the numbers in the box differs from the normal curve, the more draws are needed before the normal approximation takes hold. As an example, you can see that there's this lopsided box with 9 zeros and 1 1. So zeros are going to be much more common in the histogram here for just the box itself. And when we look across 25 draws, this doesn't quite look normal. We could see some skewing here. You can see it getting closer and closer to normal as our number of draws increases. To see this really laid out, let's look at probability histograms for the sum of 25 or 50 draws from the box 1, 2, 3. This simple box has histograms that follow the normal curve pretty well at 25 draws and at 50 draws. But what if we look at the histogram for the box 1, 2, 9? Well, this histogram is nothing like a normal curve, as you can see. And when we complete 25 draws, the histogram doesn't remotely resemble a normal curve at this point. You can see a vague trend, but clearly many more draws are needed. Even at 50 draws, this is still wavy and doesn't quite follow our normal distribution very well. But once we get up to 100 draws, now we start to see a histogram that follows a normal curve pretty well. So what's the lesson here? Well, if you want to use the probability histogram to estimate chances, you can do that when you have a sample size or a number of draws or trials that when you have enough trials or draws to have approximated the normal distribution. As you can see, when we have a box that's already follows the normal curve pretty well, the histogram, you don't need to have as many draws or as large a sample as you do when you have a box, a population that doesn't follow a normal curve in and of itself. So in that case, once you get to, it's possible that once you get to enough draws, your histogram will look like a normal curve. And so that's important to keep in mind, and we'll see that as a trend, especially in our final unit on inferential statistics. A couple of final ideas. The normal curve is tied to sums. What do we mean by sums? Well, it's literally tied to instances where you have used the sum as a primary way to consolidate or manipulate your values. The sum, adding, isn't the only thing you could do with values. As we saw in correlation, sometimes you multiply, in that case, deviations, but we use sums quite frequently because averages are a very common measure. They're very useful. And so that's how we can go from the normal curve in thinking about sums to thinking about averages, which we do quite a lot in statistics in the applied or practical real world. And what we can see on the right here are histograms that would result if instead of using sums, we were using products or multiplying. As you can see that it doesn't matter if you did 10 rolls or 25 rolls. I guarantee you if you went up to 100 rolls, you can see it doesn't matter. You'll never get to a normal distribution here. This is a different type of curve. There are a lot of curves. We're just mostly looking at the normal distribution in this class, but if you go to graduate school or do later statistics, you will definitely learn about other types of curves. One final thought. The central limit theorem is an important idea in statistics that helps us see that with enough draws, the probability histogram for the sum will be close to the normal curve. However, the histogram must be in standard units, and the number of draws needs to be reasonably large. And we will use the central limit theorem again in our next unit, even later in this unit. This is called the central limit theorem because it plays a central role in statistical theory. You might be wondering, how many draws do you need then? If the number of draws is so important, how do I know how many draws do I need? Well, this is a good question, but there's no set answer. So much depends on the contents of the box, as we'll see in our next unit on sampling. Remember that a take-home message here from this chapter is that the expected value and the standard error for a sum can be computed from the number of draws, the average of the box, and the SD of the box. And these are useful values, especially because the expected value pins the center of the probability histogram to the horizontal axis. Our expected value will be here. And the standard error fixes the spread here. So here we have one standard unit, two standard units. What is the distance here? What's the size? It's one standard error. So let's take a quick break, and when we come back, we will do some review exercises for this chapter.